Well, it's really a pleasure to be here to tell you a little bit about some of the things we've been doing in developing new membranes. And this is really a story. What I want to do is tell it to you as a story of commercialization. And so I'll tell you a couple of different materials we've made into membranes and why. And but I'll start kind of from the origin, which is how I got interested in membranes in the beginning. And it was about 10 years ago that I was reading about wells like this one. This is a well where this is a region in India where people get their water, and where in this particular region, 60% of the wells have over 5 times the World Health Organization limits for arsenic. And so that, I started getting very interested in water at that time, and we started thinking about water and ways in which you could either purify or get clean water. And one of the obvious ways is this. I love this way of looking at water because we consume water in 3D, so let's look at it in 3D. And these are the sort of water supplies on planet Earth. There's the fresh water. That's that tiny little dot there, so you can get a sense of how, the accessible fresh water, I should say, how fragile that ecosystem is. But of course, this is the big source, right? The seawater. And when you look at desalination, you can get encouraged by the growth, the dramatic growth in installed desalination capacity. But at the same time, when you look at the cost comparison between, say, desalination and groundwater, there's still a very big difference. And that's where I got kind of interested in knowing, well, what could a material scientist and engineer do? How could we contribute to this problem? Now, when you look at a desal plant, and this is a cartoon, of course, but you bring the seawater in and you pre-treat it, and then you run it through what are called reverse osmosis membranes. And then there's secondary post-treatment after that, and then you deliver the clean, the desalinated water. And when you look at the cost, why is it so expensive? What you find is that a large amount of that cost is actually in operating costs, energy consumption. And then another large amount of that cost is in upfront capital costs. But what's interesting is, as a material scientist, okay, where are the materials involved in this whole kind of complicated set of processes? And when you look at this material that's doing that very critical step of separating the salt from the salt water, that is a layer of polyamide on top of another polymer, and the active material is the polyamide. And what you see when you look at this, you see that has not changed in 50 years, that material choice. And so that's a great framework for us to say, well, is it doing the best that it can, right? Is it the best material for this job? Could we make a difference? And it becomes even more interesting when you realize that actually it's not. First of all, it's actually a pretty poor choice, except that it works and it's cheap, which sounds good, but it's really, really delicate. So what that means is, for example, if you had drinking water in the feed, that's 6 parts per million chlorine. That's actually too much for these polymers to handle. So you have to pay to have it removed in the pretreatment step, and then you add it back because you need it in your drinking water. So what we realize is that actually a lot of the costs involved. Oh, is this going to? Oh, yeah, there you go. A lot of the costs involved in the desalination actually are not just about the membrane itself, but it's about all the work around the membrane to protect it, essentially. Right? And so this is a great call to action for someone who thinks about building new materials. Now, when you think about a membrane, what we thought at the time was, well, okay, the ultimate membrane would be the thinnest possible material, right? And we were actually working with graphene, which is a 1-atom thick material right there. And we thought, well, what if you could make this material into a membrane? You might really minimize viscous losses. You might actually have other advantages that graphene has, such as resilience to chlorine and other things. And so we thought, well, okay, let's model this. And that was what we did at first. And that's compared to the thickness of polyamide. This is about 200 times thicker than what this would be if you could make it into a membrane. So we did some pretty sophisticated modeling, and this is one of the first simulations we did. And we showed actually that. So here's the dynamic simulation. These are now you can see the water molecules are trickling out, and that looks really slow, but actually it's not, because these are picoseconds. And so actually this is really fast, and it's 100 times more permeable than competing polyamide-based membranes. So this was pretty exciting. So not only could you flow water through graphene if it had a hole in it and sort of just the right way, but it would actually flow really, really quickly. Now, of course, water flow doesn't really get you what you want. You also need to be able to reject the salt. So that was the next step. And here's a salt ion. So these are salt ions. There it is. It's coming up to that same pore. Water's pouring through the pore, and the salt goes away, right? And so what we showed with these simulations is you could make this material into a selective and highly permeable membrane. And so that was actually pretty exciting. Actually, this is a movie that we enjoyed a lot. We watched this in the group like 1,000 times. Every Friday night with popcorn. That was really exciting. Now, okay, so we modeled it. Can we make it, right? And so when we started thinking about making these membranes, you know, there are different kinds of graphene. There's the picture-perfect graphene that sometimes you see, and I'm going to press the red thing, hoping it doesn't. Oh, yeah, that worked. Right? That's the picture. That's a single sheet of graphene. That's a single. It's an amazing material. Every atom in graphene is a surface atom. Right? How cool is that? Right? Just think about that. But you know, it's also hard to make it this pristine. And so when we started thinking about how we're actually going to make these things in a cost-competitive way, we realized we needed to use a different, much cheaper form, and it's kind of a messy form. What happens is you take graphite, and you basically, which is just layers of graphene, that's all graphite is, and you just oxidize it, and it's very easy and cheap to do. And then you get graphene, but it's been kind of messed up, right? So it's called graphene oxide. What's really cool about it, and these are some comparisons of you know, graphene oxide versus graphene. Graphene oxide looks like this. So now instead of just a nice pure sheet, it's actually got all this other chemical functionalization on it. But that's the thing about that is if you were doing something with electronics, which a lot of people are interested in doing with graphene, that wouldn't be good. Right? But if you want to use it as a structural template to build new membranes out of, it's fine. So here we have this really kind of great kind of tailor-made for graphene oxide application. And you know, this one kind of negative, you can't make graphene oxide as large a flake as you can a pristine graphene, but it doesn't matter because you got to make them much larger than either of these. You got to make membranes that are, you know, many square meters in area. So, so we settled on graphene oxide as our materials choice, and basically the key to unlocking this material as a membrane was actually figuring out how to lock it back together, right? And so it's kind of cool. You take graphite, you break it apart, and then you basically reassemble the fragments. That's essentially the kind of big picture of what we did, and that the key was in developing these kind of linker chemistries between sheets, because then what you have, you have this kind of this challenge. This is graphene oxide mixed up in a beaker of water. And if you just link it together without thinking about what you're doing or thinking about making a membrane, it just clumps up, which you might expect, right? So I can take all those chemistries that you see here, right? All these chemistries, and I can actually use them as handles. So this becomes a very highly tunable platform. And if you do it the right way, you can actually make it so that it's this layered material that where now the separation, the rejection happens by the spacing between these layers. So I can have like that salt water or some other solution go this way, and the spacing between these, which is controllable by this chemistry, becomes the way to reject and dictate the properties of the membrane. So it's a very tunable platform. And these are some of the most beautiful pictures I've ever seen. They were taken by our collaborators at Oak Ridge National Laboratory. And this is actually a membrane we made in the lab. This is called a transition electron microscope. So we're seeing atoms, right, with this. And this is, each of these is a real sheet of graphene oxide. And so this is a side view of our membrane. And the reason I'm showing you this is, one, because I get to show something that's incredible, and it's really like art, even though it's reality. But two, you see these are different, right? And so that, that speaks to the ability to tune them. And we can see the tunability not in the performance of the membrane itself, not just in that, but also even in the atomic scale pictures that we're able to take now of these membranes. So this is a highly tunable platform. It's got high permeability, and it's got the ability to be highly selective, right? So this is quite an interesting platform chemistry. But very importantly, we also showed in our very early experiments that these were super resilient. So now, unlike polyamide, you could take these graphene oxide membranes and soak them in chlorine overnight. highly concentrated or other organic solvents, and nothing would happen, right? They still work as a really good membrane. So these are all kind of really exciting attributes, and this is one of the very first membranes we made. We're able to filter these, anyone who makes a new nanofiltration membrane, one of the first things you do is you filter. For some reason, it's methylene blue, right? That's like the dye, everybody. So we filtered methylene blue like everybody else, and we showed that we can get 99.9% of it removed. So it's very selective for methylene blue. That's about a 1.5 nanometer particle. But importantly, it's got all these other properties, and you'll notice that I'm emphasizing the resilience as the properties on this slide, because I'm going to come back to that in a minute. Okay, now, so we had this membrane. We had demonstrated that it had these unique properties. It was made of this material that's scalable. But we were also starting to think about the application space at that time, and I'll tell you why in a minute. You sort of get, when you come back to this slide that I showed before, there's something interesting that you may have noticed. There's an inflection point there, right? And that inflection point actually happened for a couple different reasons, but one is that that's when the industry switched from thermal-based desalination to membrane-based, right? Okay. Now, why is that important? Well, that's important because, of course, as all good things that can be explained well, they can be explained with pasta, and at least an analogy with pasta. I'm a big fan of pasta, and so if you think about pasta, when you make pasta, you cook it, and then you carry out a separation between the pasta and the boiling water, different country. In this country, we tend to wait too long, and so it's overcooked. But either way, you throw it through a colander. That's actually a membrane. Right? That's a membrane. It's just got big holes. But the thing is, you could carry out the exact same separation. Right? If you wanted to carry out the same separation between the pasta and the boiling water, you can just leave it on the stove. Right? And you would actually succeed in separating the pasta from the water. Now, that would taste even worse than some restaurants I've been to. But it would still be, you would have achieved the same separation. Right? Now, the thing is, the reason I love this is not just because I love pasta, it's because you can feel the energy difference, right? You leave it on the stove, it's going to take 10 minutes, whatever, right? It's a lot more energy intensive to separate things using thermal energy than just using a membrane. And it turns out that you can save over 80-90% of that energy by switching. Now, when you look at our world and you think about our 1 to 10 nanometer pasta, right, in the world of things that need to be separated from each other, there's a whole lot of pasta at this scale that we need to separate. Right? Whether it's because we're concentrating something or because we have a mix of a bunch of complicated things and we need to separate one thing out, we do a lot of pasta boiling. Yeah, but the thing is that we do it with boiling. We don't do it with membranes. And those are distillation columns. That's what you may have seen these on the sides of roads, right? They're all over the place. These are pasta boilers. That's all they are. But you're basically using big pasta boilers to separate one tiny molecule from another. And that is really, how we do separations today. The thing is that, and this is where I think people get surprised, is when you look at how much energy and therefore CO2 emissions this takes and creates, right? So industrial separation, I apologize, this is a little bit old, but these numbers are a teeny bit different now, but this is from 2015. Industrial separation, industry as a category, industry, not separation, industry is about 1/3 of our energy consumption. But if you look at what part of that goes into boiling one molecule off another, it's 40%. So that means that about 13% of all energy, right, that we, all this precious energy is mostly derived from fossil fuels still, goes into these pasta boilers. And yet we just saw that you could save 90% of that, up to 90% of that, by switching it to a membrane-based process. But if you look at that list, it actually is very short. There's very little at the large scale that is using membranes to separate this scale chemistries. And the reason is actually quite simple. The reason is that the conditions needed to do the separations of those industrial processes, of those pastas, are too harsh for the membranes we have today to survive. Okay? So when you look at membranes that can survive harsh conditions, that's primarily not polymers. It's you know, at the large scale, you've got stainless steel, but you've also got then ceramics, where you can handle micron scale separations. But at this scale here, there's really no robust option. Right? We can use polymers like we do in desalination, but they don't work under these very harsh conditions that you need for pasta boiling of chemicals. So my students, Shreya and Brent, who are working on the experiments and some of those beautiful experimental results I showed you of the graphene-based membranes, they started to look at this more in more depth. Right? Say, okay, where could we really make a difference, and where? And when there's nothing like calling up a company and interacting with the people making decisions, right? So these are like the plant operators, right, at a desal plant, and they did that, and they did it as part of this wonderful NSF program called I-Core, that forces you to do over 100 customer interviews for your technology in different spaces. They wound up doing over 300, and they learned a tremendous amount. So we were able to map out, like, well, this is an axis of like chemical environment, less challenging, more challenging. This is the temperature resilience. So this is kind of a map of the resilience. And these are where polymers fit, polymer membranes. Those are the membranes that can handle that size scale separation, right? And you can see most of the research is right here, actually. It's mostly on water. Right? But so you have polymer membranes you can buy, you can pay extra to get them temperature resilient. You've got some emerging polymer membranes. But when they did these 300 interviews in these different industries, what they need falls way outside of what's available, right? And this becomes extremely exciting to a material scientist and engineer who's thinking about how to make materials in new ways. And this is really showing you we need resilient materials that can be applied to these different industries. Right? And so what we realized is, the membranes that we were making in this one industry, pulp and paper, in this one industry, they could have immediate value. Pulp and paper, thanks to Amazon, is a growing industry. It's growing at 3% a year, and it's 1% of all CO2 emissions is just in the pulp and paper industry. So it's a big part of that industrial separations wedge. And what we realized is that we had a real opportunity to use our membranes and tailor them for this industry. And so that's what we did. We started a company called Via Separations, CEO, CTO. We have now we now print our membranes, and we like to call our first 5K. We printed 5K of membranes at a single time. Oops. And actually our scale up is now in the tens of millions in terms of area. And here's actually one of our pilot membrane modules sitting in front of the pasta boilers at a pulp and paper plant. Right? And so this is a I think it's a really cool story of idea and atoms in a simulation all the way up to the plant. And in fact, what's cool about running at a plant for months on end is you can get real data in the field. And this is the energy consumption. This is in kilowatt hours per gallon of water treated in the pulp and paper mill. And this is in direct comparison. So you can directly compare to what the mill requires in terms of their energy. And it's about a 90% reduction. This has now been verified by DOE and other places. So there's a real immediate sort of reduction in energy, a reduction in CO2 emissions that you can get by swapping these membranes in. Now, and we're currently, this has been a very exciting run with this company, which is currently, this was the field test, the pilot I just showed you, and now we're building our first large commercial system. And that's just been very exciting to see that translation. I think there's another element to this that's important, and that is that, when I get excited about separations and the role of new membranes in that, is that, we heard a lot about things like, the CO2 in cement, right? Cement production, CO2 in steel and aluminum. These are these tough to decarbonize sectors. What's cool about separations is how they cross-cut all of these. So in many of these, in most of these, in mining and refining and chemicals, there is a massive chunk of that is related to pasta boiling, where a membrane that's targeted towards that application can make a really big difference, like I just showed you in pulp and paper. Right? So I get really excited about this, this opportunity. Now, I think there's another reason to be excited now about it, which is in, for example, and this is just one example, right? This Inflation Reduction Act, which is not going to get us to Paris, but it's going to get us closer. But the point I want to make is that there are these opportunities right now on the table, right? There's many billions of dollars on the table for technologies like the one I just showed you that can act within the next few years, right? So that's another reason to go fast and to make an impact now. Speaking of going fast, I want to point something out here. We were able to commercialize, we were able to spin a company out in 5 years from that first MD simulation. And there's some reasons for that. One reason is because of the tight coupling at every step in the way that I didn't have time to tell you between computation and experiment. It started as a computational prediction, but computation stayed in the loop at every step. Right? Also, the willingness of my students and excitement to assess markets, techno-economics, that was really important. And also the investment, the tough tech investment that we were able to get from the engine, which is right here in Cambridge, was absolutely critical in their support. And then this is the point, I want to put many discussions with industry technical teams along the way. So it wasn't just that we talked to, folks in these companies about where their challenges are, where a membrane can make a difference, but we actually sit down and talk about technical details with their teams. And I want to make that point because I think this is an ILP conference, right? And so I can't underscore the value enough of doing it this way. And I love this quote from Einstein. He says, if I were given 1 hour to save the planet, I would spend 59 minutes defining the problem and 1 minute resolving it. And one of the reasons ILP is so critical and such a perfect fit for MIT is because that's what we care about. We want to define and then solve the right problem. Right? We want to make an impact. And the only way to do that, and I think we know this and it's in our blood, is to work closely with industry. Right? And so I have this little cartoon. I think a typical way to get, you come together, you write proposals, you submit them somewhere, you get grants, and then maybe you explore a company, right? But I think the role of IAP is absolutely critical here because that allows us to have the market in the room as we think about the ideas themselves. And then as we go on to try to commercialize them, it gives us these tremendous advantages. We can enhance our understanding of product market fit. We can de-risk the venture when we go out and pitch it. There's opportunities for partnerships, obviously, and more strategic relationships when you're going after things like non-dilutive funding. So I just think this has been a tremendously important program, and I can't emphasize that enough. And they didn't pay me to say that, by the way. Okay, at all. That's genuine. Okay, now, I'll just close on this last example, because speaking of talking to companies, we've been talking a lot to folks in battery recycling. And whether you agree with this, there's a lot of debate over whether charts like this are real or how much there is to mine, et cetera. But I think everyone agrees there will be a real need for other ways to get lithium, cobalt, and nickel, among other things. And this is showing that opportunity, even if you include recycling, the gap, right, in lithium supply. So this is another one of those sort of call to actions for materials designers. And in this case, the call is a little different because here what we realize is that electrification of the membrane could play an enormous role in its performance for metals extraction. And so we had been working on these silicon-based membranes, and here's the former student who's now the CEO of this second company I'll tell you about, Brendan Smith. And he and another student, Jayden, had developed this way to make teeny tiny little holes in silicon. So people have made silicon membranes, but not with these teeny tiny holes. Remember, the pasta that matters is in that 1 to 10 nanometer size, right? And in this case, it's really tiny. It's 1 or 2 nanometers. And we were able to make these across large tiles of silicon, not really limited. It's a 2-step, very simple fabrication process that's in those papers. But what we're able to do is now show that we can make membranes repeatedly with very appealing properties in terms of resilience. So we can go to negative pH, highly acidic conditions, very high temperatures with these membranes, all while filtering, high pressures, all while filtering very tiny things. And again, what's exciting and the reason we're pulled now into this second venture is because of the fact that we have all of this robustness and we have tunable conductivity. And that's another part of the membrane that I think is really exciting on the design side, right? Membranes don't just have to filter, they can do more. In this case, it's conductive. And so we're able to show that we can remove the tiny little particles. Like I said, you got to do that just to get in the game. But we're also able to show that we can reduce. This is an example of battery recycling. We can reduce the number of steps required because we have these ultra resilient membranes. We can reduce the number of steps from 20 to 5 and take most of the thermal treatment and all that energy out. So we can really, we believe, change the game in battery recycling and primary extraction as well. So I'll end there. I see that that's blinking, and I'll just say that I love, as a material scientist and engineer, I love the fact that we named the age we live in by the material that sort of mattered in the age. I also love that we probably won't ever be able to do that again, because we are truly in this sort of era of atomic scale design. So we can now really not just put atoms where we want, as Feynman predicted in the late 50s, but we can do it at scale and inexpensively, and that's where we are. And so it's really a matter of sort of not can we do it, but what should we do to make the most impact? And that's where, again, working closely with industry makes all the difference. So I will stop there. Thank you very much.
Professor Grossman. So questions, we usually source them from Pigeonhole, so if you're getting ready to post some, please do. I think your presentation was captivating that they were not writing the questions down, but just to get it started, you mentioned connecting with industry and having them come to your lab and test out ideas and validate some of the approaches you're doing. Do you see that as something that has grown in recent years? Because probably when you're a young faculty, it's a new thing to do, and you probably have a new group, but now that your group is used to that, is that something you do more and more of and have a process for?
Absolutely, and I think it's, again, we need this. We need these partnerships. If we really want to make a difference in the space that I have been working on and care about passionately in climate sustainability, we can't do it without working together. The complexity that we have to hold in the same room is too much, and we need to know about things that we don't know about in our research groups, particularly involving scalability, but also involving localization of products or real market value proposition. That's where we have to have those partnerships. The other thing about it is, many of these companies many companies that I've worked with are going to be investing a lot of money in this space. And if you add it up across all of the sectors and large companies, it's in the trillions and trillions of dollars, right? And over the next couple of decades. And so the question is, can we work together to make sure that those investments count at least as much as we are able to make them count, right? And by the way, that's a little bit of a shameless plug for this other thing I do, which is the Climate and Sustainability Consortium. I think you heard about it this morning. But that's our approach there, right? It's to convene member companies from across the sectors and to convene them at the table of MIT in a way where we're trying to work together to go faster, right, across sectors. So you get to learn about how different sectors are approaching the problem. We get to work on those problems together, and you get to ripple the effects across sectors as well, right, in terms of impact that you make.
Something else that you touched upon in your presentation, you mentioned about, I think it's with the IRA Act here, that there's money that's put into helping accelerate some of these projects and collaborations. Could you say, and it had kind of the next 4 years, I think it mentioned there was this money available. Could you say a little more about that and what sort of opportunities that presents for industry to work with you and others here at MIT?
Yeah, I mean, I think, the government is, the government has to play a role, industry has to play a role, and I think MIT has an obligation to play a role. I think we all have to play these roles. I think this is really important money to basically test risky ideas, but also create relationships, right? Because in a lot of cases, the technologies that are coming out of labs can pair up with companies that are interested in partnering or helping to scale or even investing, but with the government willing to put their money on the table, there's a real opportunity to get more, right, for bang for your buck, and that gets everybody interested in different ways, right? And from the company, a small startup, it's non-dilutive funding. From a company that's going to work with them, it's doubling or tripling their investment. And so this is really important money. Now, the thing about this money is that you need kind of shovel-ready technology. This is not, at least this pot of money. There's other pots coming into longer-term research, which is really important. But this money that I showed you, those loan programs and things, those are really going to have to be for technologies that can scale. One of the things about membranes that's really cool about membrane technologies is they're modular. So unlike the pasta boiler, right? Anyone who's taken a chemi class knows, like, the first thing you do is you walk into class and by the end of it, you know how to spec a distillation column, right? And you also probably know it costs about $100 million or more to build. And so that's not very modular, right? If you want to expand capacity by a few percent, that's a tough call. But with membranes, you have almost unlimited modularity down to the single module, and you just stack them as much as you need. So it's very scalable. Yeah, that wasn't your question. Sorry.
No, I think so. And, but that money is in the form of government grants to researchers or to
both.
Okay, to industry.
Both.
Okay.
Yeah.
Okay. Well, it's something to think about. Yeah. Certainly, something we should all be more aware of, and how to access that.
Yeah. Oh, well, that was in the pilot, but we can tack on to any pasta boiler. You give us a pipe out of a pasta boiler, and we'll give you one back in, and you'll save energy and money. Now, what's nice about that is you don't have to know about how membranes work. If you don't use them, you don't need to know about how they work. They can be used in these kinds of contexts more as a service, or they could be used, or you can run them fully. If in food and beverage, there's a lot of membranes in use. In the dairy industry, they'll use membranes, but that's also a big pain point because, again, actually, it's for the same reason. In the dairy industry, where you're taking out things like lactose, and at those last steps, those membranes have to be cleaned by law every day. And but because they're so delicate, you can't use traditional cleaners. So you shut the plant down for about 6 hours a day to use these very specialized and costly enzymatic cleaners. So it's just an example to say, like, different industries kind of speak membrane or not, but it doesn't matter. Now, could we fully replace pasta boilers? Which is, I think, part of your question. Absolutely. It depends on the industry, though. In some cases, you'll need a little bit of boiling still. Right? That depends on the thermodynamics, which I would love to talk about, but I probably shouldn't.
Okay, I think we'll leave it there.
Yeah.
Okay, thanks,
Good.
Jeff.
Thank you. Yeah.